For Mat 8101, we're going to finish off our trig derivatives by looking at the derivative of tangent. Not the tangent line, but the tangent trig ratio. Of course, there are other trig ratios we could look at the derivatives of, such as secant, cosecant, and cotangent, but we're not. We're just going to do the main ones, and we're going to do tan right now. So we never looked at the graph of tan in level 1 math, but we'll stop and take a quick look here, but we'll focus mostly on the math because it's pretty straightforward, and if we've figured out sine and cosine, tangent won't be that different for us. That being said, the derivative of tan x is secant squared x, and the derivative of tan u, if u is a function, is secant squared u. So we recall that secant was the reciprocal of cosine, so we have it here, secant x equals 1 over cosine x, which means you could also write this as 1 over cos squared x, but we always like to keep it as simple as possible, so we use secant squared. So now, not only is it the reciprocal of cosine, it's also part of the derivative of tangent. And once again, just briefly, what are we looking at? We are looking at the graph of tan x in red, and the graph of secant squared x in blue. So noticing that tan is very, very different than sine and cosine. First of all, its range is infinite in either direction, whereas sine and cosine were kind of limited to a range between 1 and -1. But it's doing all sorts of crazy things. It seems to have asymptotes occurring every so often. And also really important, if you look at the period, the length of one cycle, and the easy point to pick is just the middle here, it goes from 0 to what is actually pi. So the period of tangent is half the period of sine and cosine. It goes through one cycle in only 180 degrees, which is quite different. And if we were to think deeply about this, of course the asymptotes are going to occur whenever we have values that are when x is equal to 90 or 270, where we want to have no run, so that would create a fraction over 0, which is an asymptote. Secant squared x, your normal secant graph would also have bumps or u's and hills on the bottom, but secant square doesn't, because we're squaring any value, and that means we will only have positives, so there will be no negatives when we have a squared graph like this. And if you really wanted to relate it to cosine, which is it goes with, cosine starts at a maximum here, goes to there here, where you get an asymptote in secant and secant squared, and then goes down to 0, where normal secant would look like this, but because it's squared, it's flipped back up, and so on and so forth. A lot of extra information, we don't need to get too into it. I'm just trying to avoid showing you how to get the derivative from first principles, because no one likes that. So we'll start pretty easy here with a couple of examples. Light chain rule, barely any, but I will go the long way. So let's say that the inner function is 5x, which we could call u. So if u is 5x, we know that u prime is 5. And let's say our outer function is for tan u. We'll call that v for tan of u. So we know that the derivative of that, we now know, is going to be 4 secant squared u, which is the same as 4 times secant squared of 5x. In order to build the total derivative, y prime, we pick up all the little pieces, and we get y prime is equal to 5 times 4, 20, onto secant squared 5x. Done and done. All right, looking at our second example. So we're bringing in some product rule. Consider this u, consider this v. U prime is 2x. V prime, a little bit faster. We're going to take the derivative of the inside. U will be a derivative of 1/2, and then you multiply that by the derivative of the outside, which is secant squared x over 2. We're not done yet. We need to remember that we do u prime v plus v prime u when we're using the product rule. Let's put it all together. Y prime equals the highlighted u prime v, 2x onto tan of x over 2 plus 1/2, x squared over 1/2. Let's put up this bad Larry and put it over 2 onto secant squared x over 2. So nothing really that different than we're working with sine and cosine. It's just the derivative is something that we're not really as familiar with as we were with the other two trig functions. And the last two quick examples. This one looks like it could be product rule in the making if we do a little work beforehand. So the derivative of sine of 5 of x, derivative of the inside u would be u prime would be 5, and then the derivative of sine 5x or sine u is going to be cosine u, so cosine 5x. Looking at the second one, our v, derivative of x squared is 2x, and the derivative of tan u is secant squared u. And then finally, when we add them together, f prime of x is equal to 5 cosine of 5x onto tangent of x squared plus 2x, and I'm just putting it in a preferred order, not that it makes any sense. That's the way I like it. Secant squared x squared. Number 2 is actually kind of gnarly. So I'm going to start with a rewrite and trying to make it clear. So we have a tangent, which is definitely on the outside. And honest to God, the first time I did this, I totally messed it up. And the tangent is of cosine of x to the power of 1/2. So going back to those fractional exponents to prepare for differentiation. Okay. So my innermost function, u, is cosine of x. So u is equal to cosine of x, which means the derivative of that is negative sine x. So now I have to keep track of a negative. Awesome. My next function, my next layer, is the power. So v is u to the power of 1/2, which means v prime is 1/2 u to the power of negative 1/2, which is 1/2 cosine x to the power of negative 1/2, which we could write as 1/2 root cosine x. And our final layer comes with the tangent. So we have w is the tangent of v, which means the derivative, w prime, is going to be secant squared v, which is equal to secant squared of u to the power of 1/2, which is equal to secant squared of root cosine x. All right, so what are we gathering up? Just kind of organizing my thoughts here. I need anything with x's, anything that I fully simplified, this guy and this one, are going into my final derivative. G prime of x is equal to, let's put the negative from the sine x, and actually we can put the sine x up top there, and then we'll have over, running out of room, 2 root cosine x, and then grabbing stuff from our last w prime secant squared root cosine x. So just watching what the question actually is, kind of figuring out how that composite function goes together is super important. And that's all the examples I need to show you. The rest of it we'll do in class, but it's just one more tool in the belt, I guess, for differentiation.